Hi everybody. So this is our first video for Chapter 13. Chapter 13 is our last chapter of the semester, and we're going to talk about acids and bases. So we've already discussed a little bit about acids and bases. We talked about neutralization reactions that occur between acids and bases. Way back in Chapter 3, we talked about how to identify and how to name acids. But in this chapter, we're going to kind of think about the some more chemical reactions of acids and bases, what they do when we make aqueous solutions out of acids and bases, and kind of their behavior. And we'll also talk about the pH scale, how to quantify the acidity or the basicity of an acidic or basic solution. Okay, so in this video, the first one, we're just going to focus on the properties of acids and bases, what they do when we dissolve them in water. So if you remember from chapter 5, when we take an ionic compound and we dissolve it in water, an ionic compound like sodium chloride, when we take that and dissolve it in water, water doesn't really participate in the reaction. It doesn't change its chemical formula. It just kind of facilitates the reaction by splitting apart the cation and the anion. When we have acids and bases in water, however, acids and bases actually react with the water to form something new. Okay, so that's what we're going to talk about first, is classifying the chemical behavior of acids and bases when we dissolve them in water. Okay, so you can see here there are a few different ways to define acids and bases. We're going to use this general definition here. Acids are compounds that give or donate H+ ions. Okay, and we'll talk about this in a second. And as a result, they produce a new ion in water called the hydronium ion, H3O+. Okay, so I'll show you the reaction in a second, but why do we call H+ ions protons? Okay, so if you remember from chapter 2, hydrogen, the element, has one proton, and it has a mass number of 1. Okay, so remember we write the isotope symbol of hydrogen like this, right? So the number on the bottom is our atomic number. That tells us how many protons there are. The number on the top, that's our mass number. That tells us protons plus neutrons. Okay, so if there's one proton and the sum of the protons and the neutrons are 1, that means it has 0 neutrons. So the hydrogen atom, when it's neutral, if it has one proton, it must also have one electron. Okay, remember those are equal when the charge is neutral. So when hydrogen forms an H+ ion, right, so when it goes from H0 to H+, right, that means it's lost its electron. It doesn't have any neutrons, so an H+ ion is literally just one little proton floating around in solution. Okay, so whenever I say whenever I say protons, I mean H+ ions. Okay, so those are interchangeable with each other. Okay, so when we take an acid and we dissolve it in water, the acid will give its H+ ion to water to make the H3O+ ion. Okay, so for example, here's a reaction of this acid here. What would be the name of this acid? This is hydrochloric acid. Okay, so hydrochloric acid reacts with water. Now see how we put water as a reactant here, whereas in dissolution reactions with ionic compounds, remember we put water up here, right, because it doesn't actually participate. So it's a little bit different here, right? So we don't do that. Why won't my thing erase? There we go. Okay, so water participates in the reaction. So our acid here, the H+ from our acid, as we go to products, is given to water, right, because acids give away their H+. Water gains a proton, so it goes from H2O to H3O, and it goes from being a neutral molecule to having a +1 charge. Okay, because remember, it's gaining a hydrogen atom, so it goes from H2 to H3, and it's gaining a charge, so it goes from a neutral molecule to a positively charged ion. Okay, so charges definitely matter here. Okay, so water becomes the hydronium ion. Now, when HCl gives away its H+, right, when it loses its H+, HCl just becomes the chloride ion. So you can see it loses an H and it goes from being a neutral molecule to having a negative charge. Okay, so overall, what happens when we put acids and bases in water, right? The acids and bases will form the hydronium ion, which is this molecule here. That's what water turns into. And the acid, we say that it forms its conjugate base. Okay, so the conjugate base of an acid is the molecule that has one less H plus than the corresponding acid on the other side. Okay, so it's what's left over after the acid has lost its H plus. Okay, so that's what's going to happen with every single acid that we see. An acid plus water makes the hydronium ion plus the conjugate base. Okay, now what about bases? Okay, so bases are kind of the opposite of acids. If acids give away protons, bases take them. Okay, so bases are compounds that accept H plus when you put them in water. And as a result, instead, they do not produce the hydronium ion, they produce something else. They produce the hydroxide ion in water. Okay, so let's take a look at a reaction between ammonia. Ammonia is a base, okay? Ammonia with water. So this we would identify as a base. So when it reacts with water, instead of giving, see how the arrow here is pointing towards water when the acid gives its proton to water? The base is going to take a proton from water. So the H plus from water is going to move to the base. It takes a proton. Water loses now an H plus, and it goes down in charge. Okay, so water turns into the hydroxide ion because it loses a hydrogen, and it goes from being 0 overall charge to -1 charge, okay, because it's losing an H plus. Okay, on the other hand, the base is taking a proton, so ammonia gains an H plus, and it gains a +1 charge. Okay, so in general, bases react with water to form the hydroxide ion and its conjugate acid. Okay, so the conjugate acid of a base has one more H plus than the corresponding base. Okay? So what we look at here, if we look at the reactions, right, the conjugate acids and bases, they're only going to differ from the respective base or acid by that one single proton. So that's all that's happening in these reactions, right? In both of these reactions, the products only differ from the reactants by the movement of that one H plus, right? So H plus always moves from the acid to the base in this case, right? So we see water here is acting as a base because it's accepting a proton. Here, right, water is giving away a proton, so it's acting as an acid, right? So the proton moves from the acid to the base. So in both of these reactions, our proton is always moving from the acid to the base. The acid could be water, or the acid could be an actual acid, right? So because water can act as both an acid and a base, we call water amphoteric, okay? Because water can act as an acid or a base depending on its chemical environment. Okay, so just focus on the fact that the only difference here is the movement of one single proton from the acid to the base. That's how the products differ from the reactants. Okay? All right. So when we talk about acids and bases, right, those are going to be the generic reactions. Those are going to be the reactions that happen every time. If we have an acid in water, we get the hydronium ion, the conjugate base. If we have a base in water, we get the hydroxide ion and the conjugate acid. Okay, but the extent to which those products are formed, the position of the equilibrium that those reactions undergo, that differs based on the strength of that acid or base. Okay, so different acids and different bases can have different strength. So the stronger the acid or the stronger the base, the further the equilibrium will be pushed towards the products. Okay, so remember that idea of the equilibrium constant and equilibrium in general we talked about in chapter 12. Right, so equilibrium is a state where reactants and products are kind of cycling between each other. but different reactions can have different positions of equilibrium. So the stronger acids and bases are going to be very product favored. However, the weaker acids and bases will be more reactant favored. Okay, so if we look at our reaction of HCl, HCl is called a strong acid because it's what's called dissociates completely, right? That bond between the hydrogen and the chlorine is completely broken. That's why we write this arrow here, right? We write it as a unidirectional arrow because what we say is that there's essentially 0 HCl left over at equilibrium, okay? So because it's a very strong acid, we're essentially saying it is completely product favored. Okay, there's only products, you know, that's not entirely true, but we can make that assumption that there's only products at equilibrium. Once equilibrium has been reached, we will only have H3O plus and chloride in our solution. We will essentially have no HCl left over. Okay, so what does that mean for the equilibrium constant for KEQ for this reaction? Is our KEQ reaction going to be very big or is it going to be very small? Well, let's write our expression out. Okay, so remember KEQ for a reaction is always equal to the product concentrations, so hydronium and chloride, divided by our reactant concentrations. Remember, we leave out pure liquids, so water does not appear in the equilibrium expression. Okay, so if we only have essentially our products at equilibrium and we only have very little, if any at all, HCl at equilibrium, what does that mean for our equilibrium constant? Well, if our numerator is really big and our denominator is really teeny tiny, right, that means that our KEQ for a strong acid is going to be much, 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 much greater than 1. And that's consistent with our conclusion of it being very product favored. Okay, so for strong acids and bases, they're going to have very large equilibrium constants, and that's what we're going to see is that we can actually classify the strength of acids and bases based on the value of their KEQ. The larger the KEQ, the stronger the acid, because the more product favored it is. Okay? All right, so here, this is a chart that you guys will have on your final exam. So all 7 of these, except this one is kind of wonky, so because see how it's got the 2 protons right there? So it behaves a little bit differently than the other ones, but all of the other 6, these 6 strong acids right here, these are all, when they react with water, are going to be essentially unidirectional, completely product favored, only form the hydronium ion in conjugate base in solution. So all 6 of these are very product favored. All 6 of these have KEQ values that are much, much, much greater than 1. Okay? So whenever you see any of these 6 acids reacting with water, you know that you're going to use your unidirectional arrow. There is no discernible equilibrium that goes on, so you just use the unidirectional arrow here. Okay? All right, and you will have this chart on your final exam. It's on that equation sheet right now, the semester-long equation sheet. It's there, okay? So we notice that we can identify acids, right? We talked about this in Chapter 3. Acids will generally have an H out in front, okay? Another type of acid that you're going to see that we've kind of come across a little bit throughout the semester are acids like acetic acid that have this COOH group on the end. Okay, so when you see that COOH group on the end, that means that this is also an acid. Okay, so 2 ways to spot acids: H out in front, COOH at the end. Okay, and this guy right here, this hydrogen, that's the one that is lost when it reacts with water, not these ones over here on the left. Okay, so the H of the COOH, that is the acidic proton of that acid. Okay, so what can we say about acetic acid? Is this going to be a strong acid or is this going to be a weak acid? Well, since it's not on this list right here, we know it's an acid, but we know it would be a weak acid. Okay, so we'll talk about how weak acids behave in a second. Okay? All right. So just to kind of continue with that, some strong bases. Okay, so the way that we can identify strong bases, what do you notice is common in all of these strong bases? Well, you notice they're all group 1 on the periodic table or group 2 on the periodic table, hydroxide salts, right? So they all have hydroxide. So these are ionic compounds. When they dissolve in water, the metal and the hydroxide ions separate from each other. We said that bases produce hydroxide in solution. So because they have hydroxide, that's what makes them basic. Okay, so strong bases will be group 1 or group 2 hydroxide salts. They dissociate completely. There's no discernible equilibrium. We use that unidirectional arrow for these as well. Okay? All right. Okay, so what I want you to do real quick, I want you to take a look at these reactants. Okay, we're going to talk about, this guy is HF. If we kind of flip back here, HF is not on our list of strong acids. So we know that HF is going to be a weak acid. Okay, so if it's a weak acid, unlike strong acids, there is an equilibrium that happens. So we're going to use those back and forth arrows. Okay, I want you to pause the video, go back and look at your notes and see if you can fill in the products for this reaction. Okay, so the only difference between this acid then from the first ones that we did with HCl, the only difference is going to be that back and forth arrow because it's a weak acid. Okay, but what's going to be the same is that an acid plus water, the acid is going to give its proton to water. So the products here are going to be the hydronium ion and the conjugate base. Okay, so make sure you take note of these charges right here because those definitely do matter. Okay, H3O neutral does not exist. Okay, so we need to write those charges on our compounds here. So you see it's the exact same reaction. The only thing that changes is the conjugate base for each acid. Okay, and because this is a weak acid, we use those back and forth arrows right here because there is an equilibrium. Okay, now, there's my highlighter there. Okay, so when we have that weak acid and weak base, the definition of that equilibrium is that this conjugate base right here can react with H3O plus and go back this way. So we have that cyclic nature happening here. Okay, so this is going to have a different KEQ value. It's not going to be very big. Let's think about how that KEQ value changes. Okay, so what would be the K expression here? See if you can write that out. Okay, so here's our K expression. Now notice that in this KEQ, I'm using sub A here. Okay, so that means nothing different. It's still the equilibrium constant, but we call it an acid dissociation constant because it refers specifically to this reaction. Okay, so it has no different meaning than the KEQ. We just say it's a special KEQ because it refers to an acid dissociating in water. Okay, so if we think about this, right, if we think about how we already said that strong acids have very, very, very high KEQs or KAs. How do we think the Ka of a weak acid would relate to the KEQ or Ka of a strong acid? Okay, so if this is a weak acid, right, where we have this back and forth going on, okay, so reactants form products, products form reactants. That probably means that for HF, compared to HCl, we probably have fewer moles of our product, and we definitely have more moles of our HF. So that means that the Ka of a weak acid is probably going to be, Ka of a weak acid is going to be smaller than the Ka of a strong acid. Okay, so we can use that Ka as a indicator of acid strength. So the larger the value of Ka is, the stronger the acid, because the stronger the acid means it's more product favored, means there's more H3O plus in our solution. Okay? All right, so here's a list of, and you don't need to memorize these, right? But we can take a look here. If we have, let's see, there's 7 weak acids here, and you can see their Ka values are all listed over here. So they're all small, right? They're all smaller than 1, so they're all reactant favored. However, the bigger values of Ka imply stronger acids. The smaller values of Ka imply much weaker acids. Okay, so there's a gradient here. So the larger the value of Ka, even if it's small, the larger the value of Ka, the stronger the acid. Okay, and we can make these same conclusions for bases. Okay, so see if you can pause the video. This is going to be a weak base. Okay, oh, one more thing that I want to tell you about bases. Okay, so we talked about how acids have that COOH group on the end. Another way that, and bases have the hydroxide for strong bases. Weak bases are going to be things that have nitrogen in them. Okay, so if you see that nitrogen hanging out, right, this is not an acid. Okay, it's got hydrogen in it, but it's not an acid. So if you see that nitrogen in your compound, you can classify that as a weak base. Okay, so see if you can pause the video and fill in this equation. So we know if this is a base, water must be acting as the acid. So your proton's going to move always from the acid to the base. Okay, so remember when bases react with water, they form hydroxide and their conjugate acid. And because this is a weak base, we use our back and forth arrow. So again, we know that our products, our reactants can form our products form our reactants. We have that cyclic nature going on in equilibrium. This is our Kb expression now, right? So we say this is a Kb expression because we're using a base dissociation constant. How do you think the Kb value will influence base strength? So does a larger Kb imply a stronger base, or does a smaller Kb imply a stronger base? Well, remember, stronger bases mean that they're more product favored, right? So a larger Kb implies a stronger base. So same trend as acids. So if we have a large Kb, we have a strong base. Okay? All right. So really quickly, let's take a look at this reaction. Okay, we're going to wrap up here in a second, right? What is the acid in this reaction, and what is the conjugate base? See if you can fill in those blanks. Okay, so if we look at what's going on here, we know that we have an acid reacting with water because we get the hydronium ion, and the thing that's left over from that acid is that conjugate base. Okay, so HNO2 is acting as our acid, and NO2 minus is its conjugate base. Remember that the conjugate base only differs from the acid by losing one proton. Okay? All right, so just a summary, what we saw, we're going to kind of fly through this real quick. So we know that acids react with water. They dissociate in water to give the hydronium ion and their conjugate base. So here is a generic overall reaction for an acid in water. Okay, so HA is just a generic acid. It could be anything, HCl, HNO3, HF, doesn't matter. The conjugate base is HA. Okay, so we said that the stronger acids produce more hydronium per mole of HA than weaker acids, right? HCl gives the same number of moles. It dissociates completely. So one HCl will give one H3O+. The weaker the acid, the smaller the number of H3O pluses we get per mole, because remember that product can go back to form more reactants. Okay, so that means that the stronger the acid, the larger the Ka. Okay, bases dissociate to give hydroxide and their conjugate acid, so a generic reaction here is a base B is going to react with water to give its conjugate acid and the hydroxide ion. Stronger bases produce more hydroxide per mole, so stronger bases will have a larger Kb. Okay? So here are some practice questions for you to make sure that you can write those reactions. We did some practice already, so I'll let you think through these. I'll put these on the Chapter 13 review, so you'll have the key for those, and we can definitely talk about this in Zoom.